Hello, my name is Catalina Fonseca and today I'm going to talk about the anatomy and the functions of the temporomandibular joint, commonly known as the TMJ. First, this is the mandibular condyle, which is the rounded end of the lower jaw. This condyle fits into the glenoid fossa, a depression in the skull. Just in front of this is the articular eminence, a bony ridge that guides jaw movement. Between these bones, we find the articular disc. This disc is crucial because the articular disc absorbs force and prevents bone-on-bone friction during movement. Now we have three main ligaments: the temporal mandibular ligament, which reinforces the capsule and prevents the jaw from moving too far backward, and two accessory ligaments, the silomandibular and sphenomandibular ligaments. Together, these ligaments limit excessive movements and protect the joint from dislocation when we open our mouths wide. Thank you.
So to continue, I am going to explain you how the jaw moves. We have two parts: osteocinematic, which is the movement of the bones, and arthrocinematic, that is which is the movement inside the joint. And so let's get started with osteocinematic. There are five main movements. The first is we have depression, which means opening the mouth to speak or chew. For example, the mandibles move downward. And to continue, the second is elevation, which means closing the mouth to bite or shower. The third is protrusions, which means moving the jaw forward to grab food. So we can say that the jaw moves forward during protrusion. The fourth is rotations, which means moving the jaw backward. And finally, we have lateral deviation, which is moving side to side to breathe food. That is why a lateral deviation occurs during chewing. So now, let's talk about arthrocinematic. This is how the joint superface move together. It has two actions. The first is rotation, and the second is where the condyle rotation. And translation, where the condyle glides forward to let the mouth open wider. For the conclusion, all these movements work together so we can eat, talk, and shower every day. So let's to continue. My classmate Vanessa to speak or talk about for the artist cinematic.
Hello, my name is Vanessa, and today I'm going to talk to you about the arthrokinematics of the temporomandibular joint. Definition to begin is the important to understand what arthrokinematics means. Arthrokinematics is defined as the movement that occurs between articular surface. In other words, it studies how bones move against each other within a joint. In our case, we will analyze how the mandibular condyle behaves inside the temporomandibular joint. Temporomandibular joint mechanics. The temporomandibular joint performs two main movements with opening the mouth. The first is the rotation, where the condyle rotates on the axis. This is the initial movement, the one that occurs when you first begin to open your mouth. The second is translation, where the condyle sees forward, which allows for the wider mouth opening. Without this movement or opening will be very limited. The biomechanical analysis. From a biomechanical point of the whip, each movement ser specific function. Rotation is functions to reduce stress, protecting the joint from damaging force. Selection distributed loans only across the temporomandibular joint. And the moment of the articular disc absorbs. And the moment of the articular disc absorbs compression, acting as natural shock absorber. These the elements work together so that the temporomandibular joint function efficiently and without injury. Crouching to conclude, I would like to summarize the most important points with three key process: rotation occurs first, relation occurs second, the disc moves with the condyle. These three concepts perfectly summary the sequence of the articular movement of the temporomandibular joint.
Well, hello everyone. Welcome to the this explication of the biomechanics of the muscle of mastication and how they work together to control mandibular movement. So, about the mastication, it's not only chewing, and we have a very complex biomechanical process that requires coordination between muscles and the temporomandibular joint and mandibular movement. So we have the main muscles involved are this side, that is masseter, temporalis, medial pterygoid, lateral pterygoid, and digastric muscle. First, the masseter muscle is one of the most important muscles for bite forces. That the main action is elevation of the mandible. Biomechanically, it generates strong vertical force during chewing and helps stabilize the jaw during occlusion. Also, we have the temporalis muscle that contributes the elevation of the mandible. However, the posterior fibers help retract the jaw. This muscle is very important because helps control mandibular position and provides coordination during the closing movements. The medial pterygoid works together with the masseter because both muscles create a muscular support around the mandible. Biomechanically, they help maintain stability and generate force during the mastication. And the lateral pterygoid has a different function compared to the other muscles because this main role is a mandibular protrusion and translation. It helps move the jaw forward and control movement for the condyle during open movement of the mouth. And we have this muscle because it's very important in temporomandibular joint biomechanics because it assists in smooth mandibular motion and lateral movement during the chewing. And the digastric muscle mainly helps depress the mandible in other words it helps open the mouth. This action is very special because this is important during the first phase of mandibular opening. From a biomechanical perspective, all these muscles must work in coordination. If one muscle does not function correctly, mandibular movement can become unstable or inefficient. And well, during the mastication, the mandible performs combined movement including elevation, depression, protrusion, retruction, and side-to-side motion. These movements allow efficient chewing and proper distribution of forces in the temporomandibular joint. So, in conclusion, these muscles of mastication are essential for a functional mandibular biomechanics because these muscles provide forces, stability, coordination, and control of the movement during daily activities such as chewing, speaking, and swallowing. Thank you.
First, the anatomy. The TMJ is a gingival joint. It allows both ginging and sliding movements. It's formed by the articulation between the mandibular condyle and the glenoid fossa of the temporal bone. Separating these two bones is the articular disc, a biconcave fibrocartilaginous structure that acts as a cushion. Under normal conditions, this disc prevents bone-on-bone friction and absorb forces. However, during stress-induced clenching, this anatomical relationship is pushed to its functional limit. For the osteokinematics, describes the gross movement of the bones. When a patient clenches their teeth, the mandible undergoes elevation. The osteokinetic movement moves the jaw upward until it reaches maximum intercuspation or peak dental occlusion. In this specific case, the teeth are firmly locked together. The osteokinetic movement becomes completely static. There is zero macroscopic movement, but a massive amount of potential energy is trapped with the skeletal system. The arthrokinematics, the movement inside the joint surfaces. Normally, as the jaw closes, the condyle undergoes a posterior rotation and a slight superior posterior slide. However, during heavy clenching, this sliding is highly restricted because the jaw cannot move any further upward due to the teeth. The condyle forces the articular disc firmly against the articular eminence. The normal lubrication of the joint is compressed outward, creating a high friction environment with the microscopic layers of the joint capsule. The myokinematics is the muscle activation. The muscular force drives this action. Mandibular clenching is powered primarily by the levator muscles, the masseter, the temporalis, and the medial pterygoid. Under psychological stress, the central nervous system triggers a sustained, hyperactive isometric contraction of these muscles. Because the muscle fibers are contracting heavily without changing their length, they act like tightly wound springs, constantly pulling the mandible upward against the cranium without a phase of relaxation. And the load distribution and compression forces, instead of distributing forces dynamically through movement, the load becomes concentrated over time. The force is directed straight up through the mandibular condyle, heavily squeezing the tiniest central zone of the articular disc against the temporal bone. This creates a peak point of maximum loads. If this stress-induced clenching is sustained, the compression exceeds the physiological tolerance of the fibrocartilage. This can lead, this can lead to disc deformation, ischemia of retrodiscal tissues, and ultimate temporomandibular disorders or TMD.